Hi, my name is Vinod Vaikuntanathan. I am a professor at the Electrical Engineering and Computer Science Department here at MIT and a principal investigator at CSAIL, the Computer Science and AI Lab. My research is in cryptography, which broadly deals with computer security and network security and generally speaking, securing our information systems. So today I'm going to be answering some of your questions. Let's get to the first question. What is homomorphic encryption? To answer that, let's first think about what encryption means. You can think about it as sort of putting your messages, your data, your emails in a box and locking it. And the point being that the only person who can unlock the box and figure out what's inside is the person with the key. So this is the kind of encryption that we use to communicate over the internet, to store our files on remote servers, and many other applications. Now, think about the world of cloud computing, where you don't just want to store your data remotely and securely. You actually want the cloud provider to compute on the encrypted data. So think about it using the analogy of the locked box. What you want is a locked box. The cloud provider can kind of like put his hands inside the box and compute and manipulate the data inside, but of course without seeing what the data is. So this sort of sounds like black magic. And in fact, that's what we thought it was in the field of cryptography for a long time. But it turns out that using advanced mathematics, this is actually possible. Can you elaborate on your contributions to the development of fully homomorphic encryption schemes, particularly the technical challenges you overcame to make these schemes more efficient and practical? Okay, so I have to tell you a little bit about how we built these fully homomorphic encryption schemes. So it turns out that a lot of the encryption schemes you use today to communicate over the internet, they rely on the hardness of problems from number theory. For example, factoring very large numbers into its constituent prime numbers. So this problem is super difficult, and it forms the basis of the RSA encryption system, the Revest-Shamir-Edelman encryption system that people use all the time today. Another problem from number theory that is hard is the discrete logarithm problem. And that again forms the basis of a lot of the encryption systems we use today. It turns out that these encryption systems really are like a locked box. So you can protect your data with it, but we don't know how to do computations with the encrypted data without opening up the box. And that's really what homomorphic encryption is about. So what we had to do is we had to come up with an entirely new kind of encryption system, which not only protects your data, but also allows computation while the data stays encrypted. And that technology uses the mathematics of lattices. And a lattice is what it sounds like to you, right? I mean, it's really a grid of points in space, except when we work with it in cryptography, it's not a two-dimensional or three-dimensional grid of points. It's really a 500 to 1,000 dimensional grid of points. And it turns out that you can use these lattices to construct new kinds of encryption schemes where you can also compute on the encrypted data. How has your research addressed this challenge of scalability in homomorphic encryption? And what recent advancements have you made to make these systems more viable for large-scale data processing? The original constructions of homomorphic encryption used these objects called ideal lattices, but it turned out that the constructions used a combination of many different mathematical tools, which not only made them pretty unwieldy to argue about their security, but also made them very inefficient, not just to compute on the encrypted data, but just to encrypt even small number of bits. So what we did is we came up with a different encryption system based on the so-called learning with errors problem, which also is related to lattices. And what that did is it created a very simple way of encrypting numbers and a very simple way of processing encrypted numbers. So for example, numbers are, when they become encrypted, they become vectors of numbers. And when you want to add two numbers, you just add the two vectors of encrypted numbers. And the same for multiplication. So whatever you want to do with plain text data, numbers, let's say, translates very naturally to operations on encrypted data. And that contributed a great deal to the efficiency of fully homomorphic encryption system. With quantum computing on the horizon, How do you see lattice-based cryptography providing a secure foundation for future cryptographic systems, and what challenges remain? Quantum computing is this emerging technology that I'm sure a lot of you have heard about. And one of the big impacts of a large-scale quantum computer, if and when it gets built, is that it will be able to break, factoring-based crypto systems and discrete logarithm-based crypto systems that we talked about just a few minutes ago. So we need new ways of encrypting data, which remain secure in the face of these futuristic threats, and lattice-based cryptography provides one such alternative. So, these encryption systems that I talked to you just now are using lattices and the learning with errors problem. For all we know, they remain secure even if a large-scale quantum computer gets built. We do have these encryption systems using lattices, which are plausibly post-quantum secure. What we need to do is two things. One, we need to keep thinking about potential quantum algorithms, also classical algorithms, that try to break these systems, because we don't really have an absolute proof of security of these systems. What we do is we try to break these systems with new and clever algorithms, and our inability to break these systems for like 10, 15 years is sort of evidence of their security, really. That's how cryptography really works in the modern day. So we have to continue putting our best minds to try to break these systems. That's one thing to do. The second thing to do is to make these systems more and more efficient, and in fact, to integrate these systems with the existing infrastructure we have today. For example, today's internet communication uses TLS, the TLS protocol, which in turn uses elliptic curve cryptography to encrypt data. How can we modify these protocols to use instead lattice-based cryptography? So that is by far not a trivial task, and that is something that we need to invest our time on. Let me switch over to an audience question. What would you consider the odds of lattice-based cryptography being post-quantum secure? Now, that's a really great question, especially in light of the last couple of months where a researcher posted a preprint paper which claimed a quantum algorithm, a quantum break of lattice-based cryptography. Now, it turned out not to be correct. The algorithm turned out not to be correct. So far, at this point, lattice-based cryptography is post-quantum secure for all we know. But the more serious point is that all cryptography we know are potentially subject to attacks, both classical and quantum. And like I said before, the only way we can be sure, more and more sure of their security, is to continue trying to attack them with the best tools and the best minds we have. And indeed, in the context of lattice-based cryptography, we've had several proposed quantum attacks against these systems over the last few years, and all of them have failed. And that sort of gives me more and more confidence that these systems are secure. But of course, we have to keep thinking about it. What are some of the most promising developments or applications you have seen in the integration of cryptography with machine learning and artificial intelligence? On the one hand, machine learning and artificial intelligence uses a ton of data. That's what they derive their power from. And this data, quite often they're distributed across multiple entities, multiple organizations. They each have incentives not to share this data. They have this data usually belongs to users, in which case you're worried about sort of protecting the privacy of the users. There are also sort of legal and economic incentives not to share this data. But on the other hand, you do want to collect all this data and learn from it. This is beneficial to the society at large. So how do we sort of make sense of this sort of opposing constraints of privacy on the one hand and being able to use the data on the other hand? Cryptographic tools can provide a partial answer to these questions. The cryptographic techniques of fully homomorphic encryption, secure multi-party computation, and differential privacy, they address different facets of this question and provide sort of parts of the answer, really. But sort of the bigger question is the new threats that AI and machine learning pose to us, the society at large. One of these threats comes from the ability to generate content, text, videos, images, which are not real. So this is the so-called deepfake problem, right? So this is a new threat model, this is a new attack surface. And the question is, what are we doing as computer scientists about it? I think Cryptography, which is a field that thinks about adversarial scenarios, sort of defines these adversarial scenarios and tries to come up with principled solutions to it, will have answers to these questions, but we really need to think about it hard and deep. What ethical considerations guide your research in cryptography, particularly in terms of privacy and security in the digital age? And how do you address potential societal impacts of your work? A lot of the tools that we develop, they are double-edged swords. We usually think about encryption as a way to protect us, users, from adversarial entities, governments, nefarious actors, other malicious entities, from eavesdropping on our communications. But encryption is also something that nefarious entities can use to communicate between themselves, making it harder for the good guys to actually detect what they are doing. But I think my solution to it is to constantly be aware that there is this dual nature in cryptographic technology, as is the case with many other technologies that we develop, and try to sort of be mindful of how the solutions we develop can be used. Now, I'm not saying that that limits my research, but it's good to be aware of the ethical implications and all the ways that our tools can be used. What originally inspired you to specialize in cryptography, and what aspects of your work keep you passionate about this field today? Okay, so the way I started in cryptography was pretty serendipitous. I was a sophomore undergrad and done with all my coursework. I went to my professor and said, well, why don't you give me something to do? And he picked up this book, this giant book on Introduction to Cryptography, written by Shafi Golwasser, who's right here, who's a cryptographer at MIT, and Mihir Bellare. And he said, well, why don't you go read this book, start to finish, and come back to me when you're done. I think he was secretly hoping that I'd never come back, but I did. The field, the problems, they were so interesting and so captivating that it's hard not to be drawn to it. Cryptography, and cryptographic problems are full of, these characters like Alice and Bob. They're talking to each other, or they want to talk to each other, but they can't. There's coin flipping. I want to toss a coin that you cannot influence. They're trying to sort of compute together while hiding things from each other. They're trying to prove, Alice is trying to prove something to Bob while not revealing information. It's really, there's a lot of personality there. There's also a lot of mathematics that goes into these solutions. Not just sort of like thinking about these problems, but really mathematically, rigorously defining what privacy and security and fairness and robustness mean, and actually using mathematical tools to achieve solutions to these problems. So that was very captivating. And really sort of what keeps me interested is the interaction between cryptography and broadly sciences, and in particular computer science, in particular theory of computer science. There are lots of notions in theoretical computer science that draw inspiration from, sort of direct inspiration from cryptography. An example is pseudorandomness. These are sort of like, pseudorandomness is talks about sort of numbers or strings that are not random, but they look random, right? So this is a very useful notion in theoretical computer science, and it really came up by thinking about security and cryptography. And this sort of like connection is really kind of two-way. We take problems from the real world and solve it using mathematics. And the mathematics we develop actually imply sort of new notions and concepts in computer science. So this two-way street really is very exciting, and it keeps me engaged. Let's swing back to the audience questions. Using quantum computing, how can we develop a new model for cryptography that uses quantum properties for security while ensuring compatibility with existing classical systems? The interface between quantum computing and cryptography really kind of leads to two fields, I think. The first one is the field of post-quantum cryptography, which is really kind of like designing classical crypto systems, so using the infrastructure we currently have, while protecting against quantum adversaries, right? So this is sort of the whole thing about lattices and lattice-based cryptography that we already talked about. So that's number one. The other kind of facet of this is quantum cryptography, which uses the power of quantum computing. So this just assumes that we all have quantum infrastructure at hand. Our networks can sort of transport quantum states. How do we use that for security? So that's a really interesting question. Quantum computing, like many technologies, is a double-edged sword. On the one hand, quantum computing and large-scale quantum computers can break existing crypto systems. But on the other hand, if we all had quantum computers, we could actually exchange information more securely than we are doing right now. So this leads to the notion of quantum key distribution, which is a way to use quantum states to exchange secret messages. It also leads to a much broader field of quantum cryptography, which uses either quantum communication or quantum computation or both to actually achieve cryptographic tasks like encryption, digital signatures, secure computation, better than what we can do with classical systems. So that is a really kind of like a new, emerging, super exciting field that a lot of people are investigating at this point. For example, one of my colleagues and I just recently finished teaching a class on quantum cryptography at this point. It's one of the first classes of this type sort of all over the world, and it was super exciting. It was really sort of technology at the cutting edge of research at this point. For students who want to work in cryptography, how do they get into it? What core skills and knowledge do you consider essential? So I think by far the biggest sort of skill set that you need is really mathematics and theoretical computer science. So you need to actually know what computation means. You need to know how to argue about the complexity of computation. So that would involve at MIT taking 6 1220 or 6 1400, the classes on algorithms and complexity theory, and generally having facility with mathematical concepts. I think that's really the most important thing that you need to develop in order to kind of start thinking about cryptography. At what point do you become a cryptographer, and what does one do all day? I'm still figuring out how to be a cryptographer, but what does one do all day? A cryptographer is a machine that turns coffee into crypto systems, and that's hopefully what I do for at least part of my day. All right, final question. If you had to choose just one manual, which one would you choose to learn cryptography from scratch? Any other recommended reading for beginners? Okay, what I would start with is probably what I started with 22 years ago, which was the lecture notes of Shafi Golbasar and Meher Belare. But there are a lot more resources at this point. On the one hand, there's actually the internet, and there are lots of sort of lecture videos on YouTube that you can tap into. For books, a really great book is a book called The Joy of Cryptography. It's written by Professor Mike Rosulek. It really kind of starts introducing cryptography from the very basics, but is also pretty rigorous, and it doesn't pull any punches. So that's it. I really enjoyed your questions. Hopefully you learned a little bit, and see you next time.